And now I would invite our chair of the day, Dimitrios, to come to the podium and take over the meeting.
Hello, and thank you, President Catherine. We're very honored to welcome Professor Alan Duffy as our keynote speaker today. As the Vice-Chancellor of Flagship Initiatives at Swinburne University, Professor Duffy drives large-scale transdisciplinary research collaborations across universities, government, industry, and NGOs. He was the inaugural director of the Space Technology and Industry Institute at Swinburne, leveraging space solutions for real-world challenges. He is also a chief investigator in the ARC Center of Excellence of Dark Matter Particle Physics, using various techniques to uncover the universe's greatest mysteries. Beyond academia, Professor Duffy is the co-founder and CEO of Detect, a spin-off using space particles for applications in mining and infrastructure safety. He's also a passionate science communicator with over 300 TV appearances and 440 radio interviews today. He's one of Australia's best-known scientists. Please join me to welcoming Professor Alan Duffy.
All right. Yes, some light AV efforts now. Let's see if it will all work as we test it. Oh no, I have to rejoin the meeting. I might just need the meeting passcode. Thank you. But yes, I'll be trying to provide a brief and highly selective history of Australia's involvement in space, particularly around the moon. This is timely because we're going back. I hope everyone's aware of this. I'll share more, and we have an interesting role to play as Australia in that return. Let me just remove my video. Okay. Now we have echo. Echo. But there we go. No. Okay. Luckily, I don't mind the sign. That's 440 interviews. Oh, my microphone, of course. Thank you, Jared. That's right. You can trust me to find space tech solutions for your companies. Now, here we go. Sharing that and all right, wonderful. Hopefully, we'll expand that out. So, as I mentioned, we are going back to the moon, and the operative word is back. Australia has played a role in space, particularly supporting NASA in its lunar ambitions since the early 60s. The importance of this for Australia, however, is not just the wonderful technologies we've developed, the spin-out opportunities, and of course, the scientific discoveries, but it is also the inspirational value to generations of scientists and engineers who still to this day will remark about the Apollo mission as a signature moment in their lives. I have been inspired by it. Of course, I'm many decades since the moon landings. This is why I hope in this return to the moon that we will see a similar inspiration, because our nation needs more scientists, technologists, engineers, not fewer, as we seek to combat challenges that I think are familiar to all of us. Noting we had an acknowledgement earlier, but I'd like to pay my respect to the Wurundjeri people of the Kulin Nation, on whose lands my campus is based and my research is undertaken. So yes, if we cast our minds back, it was of course over half a century ago that we had the Saturn V or Saturn V rocket off to the moon, carrying the astronauts on the moon lander to the surface, and of course this iconic image. I love this image because it reminds us that, let's be honest, most of the space race was about prestige, was about demonstrating that one technological and governmental organizing principle was superior to another. Happily, science did play a role in this. Perhaps not as well known, however, is Australia's role in this monumental success. And that is because Australia has always had a supporting role for NASA in monitoring its space missions, for the simple fact that the world is round. This still comes as a shock to many people. Happily, I hope not in this room, but I get frequent replies to my posts online, reminding me of how silly I am, that in fact the Earth is flat. We know it's round for one reason, because as we turn, we are unable to see the same bit of the sky, and that includes the moon. So if you have a mission to the moon, you'll be recording the transmissions, talking to the astronauts with a facility in, say, Goldstone in the US. As the world turns, you need another telescope to pick up that communication relay. And in fact, NASA has 3 that are 8 hours apart, as it were, on the globe. And one of those is in Canberra. So we, to this day, have the NASA Deep Space Communications Complex operated by the CSIRO. Back in the late 60s, however, we had these 2 iconic facilities, Honeysuckle Creek, and everyone knows this one, right? Parkes, yes, the dish. And as they were doing, they were receiving the signals from the lunar surface, as they had been doing for many days of the mission before. However, upon landing on the surface, Neil Armstrong was supposed to have a sleep, a 6-hour sleep, roughly speaking. Now, he was clearly a little overexcited and couldn't manage to get to sleep. So said, to heck with this, I'm going out. The problem is the world got in the way. And there was an issue where Goldstone was struggling to pick up the signal. Because he left early, there was this incredible moment, just a few minutes of time in which both facilities, the US and Australia, were watching the moon at the same time, picking up the signal at the same time. And that's important because that's what NASA saw. Can anyone even see this? Can you make this out? This is Neil Armstrong. NASA was broadcasting this to the world. At this moment, in Houston, the world's TV cameras were looking at a wall. This is how they did this back in the day without digital. They projected the live images from the moon onto a wall, and TV cameras were looking at that and broadcasting that out to the world. And I think it's fair to say everyone was a little underwhelmed. NASA's frantically trying to understand what's going wrong with the image from the lander that's being relayed through Goldstone. Happily, someone's noticed that Honeysuckle Creek, so not Parkes, by the way, Honeysuckle Creek, the smaller dish, was broadcasting, and it was broadcasting this. So Australia's signal, they quickly switched to Australia's signal, and this is what they picked up. I knew it wouldn't work. It's moving. So we were able to get the live footage from the lunar surface thanks to Australia's facilities watching. Now, NASA did figure out why the image was so awful from Goldstone. They recorded the actual data, they cleaned it up, and then rebroadcast afterwards the proper version that everyone has since seen. But the fact that we got to see it live, grainy as it was because of Australia. Now, I like this little detour just to remind people that, as I said, it was about prestige. It was about national, very much a superpower-driven race, but there was also science. So this is the, but also no matter who you are, even an astronaut, you don't get to escape bureaucracy. And this is the actual incoming declaration that they had to fill in at customs, which I love. So I'll zoom in. Departure from moon. Anything to declare? Moon rocks. So just absolutely phenomenal. And that's important because, in fact, this was around, at least one of the outcomes was a great deal of science. We had large amounts of samples. In fact, one of the last astronauts was a trained geologist. They were selecting of the lunar surface to better understand its origins. And here are some wonderful shots from the surface. Remember, by the way, the dust, the sheer amount of dust everywhere. We'll get back to that. Perhaps not widely known is that when those samples were collected, they were ferried off to the world expert in geology, which was ANU's Dr. Ross Taylor, notably passed away just 2 years ago. He was flown over to the US with all the gear, as you see, and he analyzed NASA's lunar rock samples all through the night. And in the morning, they broadcast the results nationally. What had they discovered? And then he did it again that night and again. And every morning for nearly 2 weeks, national broadcasts about what they discovered from the rocks of the moon. Now, I like to think that the achievement of getting to the lunar surface is rightly regarded as one of humanity's greatest achievements. I would argue a close second is getting that many people to listen every morning to a geology lecture. But that's how inspiring the moon is. And I take comfort in that. Now, one of the extraordinary discoveries is that the moon is not the moon at all, but rather the Earth. And that because of our shared crystals, shared minerals from both the Earth and what they discovered on the moon. We believe some 4 billion years ago, Theia, a hypothetical planet about the size of Mars, crashed into the then young Earth, tearing a huge chunk of material off that swirled around. The debris under its own gravity came back together to form the moon. And we have co-evolved ever since. Now, as I've mentioned, we are going back to the moon. So the sister of Apollo, and of course the Apollo mission in the 60s, the sister is Artemis. And this is very fitting because now we will see on Project Artemis, the first woman and person of color will walk on the moon. That is the intention of Artemis writing that, I think, historic wrong when we reflect on For All Humanity. There was a notable lack of humanity's demographics in those footsteps. The mission has evolved significantly. We will be undertaking a wide range of science. For one, we'll get 4K streamed video off the surface of the moon rather than that grainy stuff we saw earlier. And Australia is still part of that critical network receiving those signals. However, times have changed. And what we have learned about the moon is that it is not the dusty, dry place that we thought it was. In fact, it has water. This is water ice at the South Pole, huge reservoirs of it, entirely, quite unexpectedly, rich in water. And that's important because by the time you have blasted off to the moon, spending all of that energy to reach it, the literal rocket fuel as it costs, of course, the bottle of water you have taken with you on that mission is worth more than its weight in gold by the time you've got there. So if you can use the resources of the moon, it's extraordinarily cost-effective versus shipping everything you need to our nearest neighbor. You, of course, don't just drink, however, that water. You can use electrolysis, so solar panels can split the water into its component parts, hydrogen and oxygen, and that's actual rocket fuel. So this new era of lunar exploration is about turning the moon into a resupply, indeed a refueling station for further exploration of our solar system, as well as to use those resources to perhaps support our expansion as well into space. And that is Australia's role that is a little different to last time around. We will be going to the moon. We don't have human flight. However, we have this wonderful campaign that the Australian Space Agency undertook, in which they are sending a lunar rover, hitching a ride, as it were, on Project Artemis. And they will be undertaking some science on the moon. They asked the public what we should call the lunar rover. And the public voted and came up with Rover, which I don't hate. It's not quite the extraordinary, inspiring name that a lot, of course, the US facilities tend to be called, but Rover is going to go to the moon in a few years' time. It is a project undertaken by the ELO2 consortium. Very proud to say Swinburne is a part of that. Our role will be developing some of the mechanical protection aspects, particularly coatings to remove the impact of the dust on the rover. That dust is incredibly abrasive. It gets into machinery, it wears it away. It is incredibly toxic. We really, it is a massive challenge to try to have a unit move around on the surface of the moon for, in this instance, 2 weeks. So we'll be testing out a lot of technology. But this consortium is putting the rover together because they want to test the ability to mine the moon. So this is the concept demo unit, and that's a little scoop. One of the intentions of the mission is to have an autonomous, so that is self-directed robot that will drive along the surface, that will extract some materials, so digging the dust, perhaps water ice if we're so fortunate, and send that back to a processing station. So demonstrating the ability to access the resources of the moon. Now, mining the moon is not without some, I think, ethical considerations. So Swinburne has also pursued technology development in minimizing the impact of those extraction mechanisms, as well as supporting ethics and law PhDs on the consideration of space, what we term in situ resource utilization. So the use of the moon and other heavenly bodies for private or national gain. So we are worrying about the challenges that this new exciting era may pose before those challenges arise. Let's learn from what we've done on Earth. Let's get it right on the moon. As I mentioned, we have a range also of building materials on the moon. So in this, the blue is titanium, the iron-rich sands are in red. So there are some wonderful building materials. And at Swinburne, we have a very large team who have explored how to build lunar steel from the regolith of the moon. And that's what makes this new era of exploration so exciting. It is no longer to walk on the moon, but rather to work on it, where we will build habitats, we'll have autonomous rovers and other vehicles doing a lot of the dangerous, heavy work, but there's no substitute for a human presence trying to learn more about the moon. And we really do have so much more to learn about it. There are still mysteries on the moon. The details of the origin of the moon, and hence ourselves, is still at a high level understood. The details, very much not. So there's a lot to learn, as well as those opportunities to use the moon to go further. Now, that's just a bit cheeky. All right. But yes, so at Swinburne, my Vice-Chancellor likes us to think big and bold and ambitious. So we will have a Swinburne flag on the moon. We will beat Monash to that. But I actually smuggled a flag already on one of those, on a tiny mission, but I think it got removed. So unfortunately, we'll have to see what the Space Agency lets us do. I want to change gears. Now, one of the wonderful successes, of course, of Rotary is in the support of education. We heard earlier this incredible program. We're going to talk to you about this, about engaging in STEM. It is a passion of mine as well. And one of the challenges we face in this new era of space exploration is the radiation. There's an enormous amount of radiation in space. There are other reasons in Australia that we are hearing about radiation sciences becoming a critical need. However, by the time my students get to me in first year physics, that is almost always the first time they have ever actually had a radiation science experiment for real, by which I mean using an actual Geiger counter with a radioactive isotope. Their entire schooling, we teach them radiation science and all the wonderful high energy physics from a book, because OH&S means we just can't put radioisotopes in a classroom. We can all have a discussion about that separately, that specific point about the OHS rules, but that is the world that we live in. So how do we accommodate the educational system as it exists in Australia, but ensure that we have a new generation of students who are able to, through hands-on experimentation, learn about radiation sciences and other advanced physics? This is the challenge that my colleagues at Swinburne set me. They heard about my initiatives with high energy particles from space, known as muons. These are naturally occurring. Through each and every one of you, there's about 200 colliding a second. So those muons are used to take X-ray-like scans of mine sites. That's the spin-off that was mentioned earlier by my colleague Dimitris. However, my fellow lecturers in physics wanted to know, could we do something with this for the lab? Even though we can have radiation sources in labs, it's still a pain to do the paperwork. So can we get around that? Can we use naturally occurring radiation? And that's exactly what we've done. We've developed a spin-out detector. Rather than try to plug this in and try to screen share, I've got a recording, but here it is, one I made earlier. This is a muon detector by which a particle travels through the top and the bottom, triggering the detector, and we record the information as I'm about to show you. This is the foundational basis for a range of experiments for computer science, maths, as well as physics that we have in classrooms across the country. We have just produced our 70th detector. This is not the reason I spun out a company, I can tell you right now. It's a terrible margin, EdTech, but it is deeply fulfilling because now I have students across the country who are getting hands-on experience with radiation sciences. The control box sits there and it just plugs into the laptop as shown. So we have our units plugged into the laptop. And what actually happens is they just simply connect the device. And then slowly over time, the events are recorded and come through, and then the students can save that to their local desktop for exploration with the teachers. Now we have everything curriculum aligned, lesson plan materials, to also empower the teachers as well. One of the challenges we were faced with is the lack of investment in these kinds of physics lessons has meant we now also have a generation of teachers who are unable to teach this. And this is part of our initiative, is also to try to, through professional development, freely given professional development courses, we're actually trying to raise the capacity of our teachers nationally, as well as, of course, engaging with their students through these kinds of experiments. We teach a range of sciences. Fun fact, the reason those particles are making it to ground at all is an example of Einstein's special relativity. It's the only way you can teach special relativity in the classroom with a hands-on experiment. But there's a range of potential national needs for this program, but I fundamentally just think it's cool. And next month, we're going to launch MNetwork. We are going to connect up all of those detectors in a nation-spanning virtual cosmic ray detector program. At this point, we can do some extraordinary kinds of science. Most importantly, we connect young people around the country who care about science, who want to do this kind of physics. There may only be, in some of our regional partners, one class has six students. I want them to know that there's at least 600 more who are logging in at that moment online to engage them, to make sure that they follow this pathway into STEM. I just want to thank our first adopters of the program, these are being used in universities across the country as well as in the schools, and is very much with the support of the Australian Research Council that believed in us undertaking something as fantastic as teaching hands-on experimentation with particles from space. So I want to close with a consideration that the demographic boost that we saw when we first went to the moon, a generation of scientists and engineers, the technologies that were spun out, the galvanizing of a nation. We cannot expect the same unless we invest. I would encourage you to remind your communities and your national leaders that the fact that Apollo turbocharged the US and allowed a generation of engineers to be able to then solve environmental challenges and other issues that arose in the 70s and 80s later, we can do the same with Artemis, but only if we support those younger generations in actually gaining the hands-on experience and learning of the fields of STEM. We can't just walk on the moon and expect it's going to solve our problems on Earth. We can be inspired by that moment and then do the hard work to save our planet. Thank you very much.
So we have some time for questions. So I would like to ask anyone who'd like to ask a question to stand and clearly state your name before asking your question. And online questions can also signal or post in the chat if they would like to ask a question. So Microsoft's microphone is around. So, all right,
yeah. Well, thank you, Alan. My name's Adrian Nelson. You touched on ethics at one point during your talk. In a week where China is expanding its bases on Antarctica, if we're on the moon doing research and accessing materials, how do you see that working? Who should get access to what?
Yes, this is a great question. So our all of the spacefaring nations have signed what is known as the Outer Space Treaty, and that bans the nations from claiming the moon and other heavenly bodies. There was the Moon Treaty later on, which said that we will share the benefits of the moon for all humanity. Similar to how Antarctica was considered a protected location beyond any one nation's claim, and any learnings and benefits would be shared. Unfortunately, the spacefaring nations didn't sign that. Everyone else has signed that, by the way, but what does that matter? Australia, however, is the only nation that has signed the Moon Treaty that binds us to ensuring that the benefits of the moon are shared with the world. There's a big tilde, as to how that happens, but at least in principle. We have also, however, signed the Artemis Accords, and the NASA-driven program that in its definition has the access and utilization of the resources of the moon. So we have an opportunity, and indeed actually a legal obligation, to do both, to demonstrate how you can use those resources in a manner that benefits humanity. Now, excuse me, let me get this right. Yesterday, we had a successful landing by a space company, a private company on the moon. Tomorrow, we will have Intuitive Machines try their second. They did a decent landing the first time around, but they'll nail it the second time. They have mining equipment on board. So while it's wonderful that there are nations like Australia who want to do an ethical, sustainable manner to the resource utilization of the moon, it's not a race anymore between superpowers. It's between startups. The private companies have beat NASA to the return to the moon, and they brought mining equipment. Now, I think this is why it matters that we have Australia leaning in. If you're not at the table, you don't have a voice at the table, right? I mean, we must be driving the development of technologies and principles for the sustainable and safe exploration and extraction of resources on the moon. If we don't show the world how to do it, we'll end up with a Silicon Valley-esque approach, right? Move fast, break stuff. That's not the way we should be treating our nearest neighbor. If for no other reason, there's also deep indigenous First Nations value attached to the moon. So from a heritage point of view, it is, of course, for all humanity, but it is particularly pronounced for First Nations. Now, this is why, and this is not always, I think, a universally acknowledged statement, but Australia's mining companies have some of the most stringent regulation of any on the world. They're certainly under the microscope in a way that most other companies are not, certainly the startups. So I'm actually quite relieved that they are, at least Rio Tinto is looking in, and Woodside as well, and Fugro are looking into how to safely, sustainably access those resources and not cause the devastation that a lot, quite frankly, of the startups will just not care about causing. The most important thing is we have government that gets over what I call the giggle factor. I brought this up in Canberra, and they look at me like I'm mad. It's like I'm worrying about traffic jams on Mars. Mining company, a startup with mining gear landed yesterday. They're not laughing now. But because we didn't push for this earlier, we're 2 years off from having our rover. We don't have the say that we should, or the ability to lead, to demonstrate how, and then share those technologies, how to do the extraction in a manner that doesn't cause the devastation that, if we don't carefully remove the dust and ice, may well happen. So I think it is our legal obligation, as I mentioned, as the unique signatory of both the Artemis Accords and the Moon Treaty, to show to the world and to benefit the world through the utilization of the moon.
Bruce Livet.
Yep.
We've been fascinated for many years about the dark side of the moon and
far side. Yes, yes.
Oh, closer. Yeah. Okay. So it's been a fascination what is on the dark side of the moon. And I understand that the Chinese visited the dark side of the moon and collected rocks. Given what you told us in the beginning, that the moon and the Earth have a common geological origin, what do you expect to find different on the moon surface than we already have here?
Yeah, that's very good. Just a point of making sure that's the album. The Far Side of the Moon is where they explored. It looks very different, for a starter. It looks, in fact, if you when you see the image, it is a completely different lunar landscape than the one we're familiar with. It speaks to a different geological history. There were lava flows across the surface of the moon. The fact that we have the near side facing us has meant that it's had different gravitational experience because of what we cause tides in the moon, the same way the moon causes tides on Earth. So we have different amounts of material that's been bubbling up, as it were, from inside. There are different asteroid or comet collisions on the different sides. So there's a range of differences that will, we hope, allow us to begin to tease out what is common to both and what is a consequence, excuse me, of their different evolutionary experiences, as it were. So we will learn, I suspect, a lot more about the origin of the moon, particularly the details of how the planetary collision occurred is actually still incredibly combative in talks. Did it, was it a glancing, but it just sounds like this doesn't matter, by the way, but it really matters. Somebody spent a lifetime on it. Is it a glancing blow, or did it hit directly in the middle? Is the core still there? Is the core in our Earth? Those are some of the details that we want to learn about. The most important reason, however, that the Chinese did this is because it was hard. To get to the far side of the moon, you need to have set up a communications relay system to bounce the signal back to the surface. Now, that's not easy, and then to do an autonomous landing is even harder. You're out of direct line of sight of the Earth. However, in doing that, quite brilliantly, they've established the first communication setup to support further expansion on the moon. It was for science, but there was a geostrategic benefit in doing that incredibly challenging mission as well. So we'll certainly learn about science, but I think in the next 20 years, we'll also learn about what were some of the other reasons as well. Oh, we've run out of time. All right, sorry, everyone. All right.
We don't have more time, but I'd like to thank you so much for your contribution and your inspirational presentation. And this is a small token of appreciation from us. Thank you.
Thank you.